from Sony Computer Science Lab, Sapienza Università di Roma, and the Complexity Science Hub Vienna. The talk will be about optimal learning paths in information networks.
Thank you, Massimo. Thanks a lot for the introduction and also, mainly for the invitation. Let me just share my screen here. Okay, I hope you can see the slides now. Okay, so it's a real pleasure to be here. I'm not really part of the community, though actually I have extensive interest in teaching education and also the theoretical science behind this. And today actually is a very modest contribution. I wanted just to share with you, some work we did a few years back. I think, it didn't, so probably we didn't, follow up as the subject deserved, in the last 2 or 3 years. But I guess, it would be interesting to share again with you and perhaps see, what you all think about this and whether you can see possible synergies for the next future. So as you can see from my title, the idea is looking for learning paths and how we can construct this learning paths. Let me start with the quotation I like a lot from Ken Robinson. This was already back in 2006. It was thinking about children retiring in 2065. And of course, the idea was nobody has a clue, what the world will look like in 5 years' time. Imagine in 60 years. So, it's clear that we cannot train people, for the jobs they're supposed to have. In 30 or 40 years, we are supposed to train people to train themselves. So learning, how to learn. So it's a sort of double concept. And this will imply that there will be a sort of interplay between the teacher and the students, a very active role of students in this situation. So whenever we try to learn something, but more in general, whenever we treat, information, we're actually moving in a space, which of course, is not a physical space. And I would say, for physical spaces, we all know, we have compasses and navigators, to tell us, how to get somewhere, and also what is the most pleasant journey in this direction. This is not the same for conceptual spaces, because of course, we don't know, where we are, in the conceptual space, provided we know what a conceptual space is. And more than this, we don't know how to move, in this space, how to get from A to B, provided we know, what B means. So the point is, of course, very important. Here, I just reported a couple of sentences from the EU programs. And also, it's interesting to look at this Obama discourse in 2009 was actually, triggering somehow the development of learning software effective as a private tutor. Somehow the idea was to go toward a sort of personalized education. And of course, there are a lot of websites now, devoted to this one. Perhaps this is a very old list, the Khan Academy, but then of course you can go for the Anki with flashcards, Duolingo, many of them actually. So the idea is how we can get these tools to get, the learning, innovative, and innovative, will have a specific meaning in a second, and personalized. So let's see, in a very simple way, how we can define a learning path. So I apologize in advance because whatever we'll be saying will be very simplistic. Still, I guess there is an interest in performing all this. So the point is, whenever we follow a learning path, I guess we can basically define, a sequence of 2 possible operations. So one operation is repetition. So we have a concept, we try to repeat, in our mind, this concept just to fix it. And the other side, there is an innovation process, which is, introducing new units and new concepts at very different level. And so, I guess one of the big questions is, what is the best sequence of repetition and innovation? Provided you know, what is the list of units you want to learn? For instance, a series of flashcards, but of course can be much more complex than this. So I will be saying something about what is known, from cognitive sciences about this. And there is, of course, the traditional results by Ebbinghaus in 2 centuries ago almost. So one is the spacing effect. The spacing effect is whenever you have to repeat something, I mean, it's not always worthwhile to repeat immediately. You have to space, I mean, the repetition. Otherwise, it's not very, very effective. And the other one is the lag effect. So the intervals of repetition can actually increase over time. Okay, so the first time I have to repeat after, I don't know, a week, but the second time can actually repeat after 2 weeks, 3 weeks, and so on and so forth. And this time, I mean, of repetition is expanding over time. Actually, there was, I mean, in 2012, a very interesting paper by Novikov, Kleinberg, and Strogatz, taking precisely this idea and trying to find from the mathematical point of view what is the best sequencing of action, provided you know what are the units you want to introduce. The idea is very simple. So take, I mean, the 0 time. So this is a timeline. So 0 here means, I mean, the introduction of the last concept. Okay. Then, of course, I mean, there is a period which is marked here in blue, in which, I mean, there is no benefit from reviewing the same concept. Okay. But then, I mean, from time AK to BK, I mean, there is the optimal review time. It means you can actually start reviewing after AK, but you cannot review after BK, because after this, there will be a forgetting. So somehow you have a useful window from AK to BK to review what you learned already. And the reason why AK and BK have this K index is because, I mean, this AK and BK can actually change depending on K. A K is the number of repetitions or reviewing sessions for the same concepts. And of course, this can be function, can be polynomial, can be exponential function of K, but this will not change, I mean, the general conclusion. Of course, we can think about very different learning procedures. I mean, something like lifelong learning, in which we want to acquire something, I mean, to be there, I mean, for the rest of our life, or cramming, which is quite typical for students. I mean, put together a lot of information in a finite time, okay, for a specific deadline, and then probably forgetting everything after. And of course, the metaphor, I mean, coming to my mind is the one of the Chinese dishes. So every unit is the Chinese dish, I mean, and of course should be spinning, but at some point, I mean, after BK or immediately before BK, I mean, this dish starts wobbling, okay, and of course you get afraid that the dish will fall, and you have to respin it. So reviewing in this case would be like respinning a specific dish which is about to fall, and introducing a new dish means introducing a new unit, I mean, to be learned. And of course, I mean, the idea of the perfect learning is to increase the number of dishes, in this case, keeping all the dishes running and spinning at the same time. Okay, so the modeling scheme is very simple. So here you have, again, I mean, top the timeline. So the question mark is because you have to introduce at each time step a new unit. So either reviewing what has been already introduced in the past or introducing a new item. Okay, and the point here is that for each repetition, you have to check, I mean, what is the unit to be repeated, because each of these units would be a different let's say, learning age, okay? So at different distances from forgetting, so you should take care of not forgetting everything. And of course, if you are in a quiet situation in which you don't forget anything, then you can think about introducing new items. I don't go, I mean, into the details of the mathematics, which is very simple, I mean, but the general idea, I mean, is quite straightforward. So this was the original idea of Strogatz, Kleinberg, and Novikov. And but in their case, I mean, the number of units to be learned were totally independent. And of course, we know, I mean, also from the previous talks that we have conceptual networks and all the units are interrelated, I mean, very strongly. So the point is, can we actually expand? So the question we had at the beginning was, can actually we expand this kind of approach in order to take into account the structure of conceptual networks? Of course, we know, I mean, about these conceptual networks. This network in particular is the outcome of the experiment that Massimo already mentioned, not specifically this one, but the general type of experiments, so word association experiments. This is probably one of the massive, the largest experiment done, I mean, back probably 10 years ago, okay. I guess it's still running. If you go on www.humanbraincloud.com, it's still running. You can actually play. And the idea was very simple. It was like a game. You're supposed, I mean, you're queued with a specific word, and then you're supposed to write, I mean, the first word coming to your mind. There was a system of filtering, so I don't go into the details. I mean, there was a lot of stuff to avoid insults and bad words in the system, but also to introduce, I mean, new words to be cued to other players, and this, I mean, helped to construct probably the largest database about word association. We also compared this with regular, I mean, databases compiled by linguists, and I guess there were a very strong overlap in terms of local properties. So the question now is, I mean, suppose now you have this conceptual network. Okay, can we optimize the learning path in the sense, I mean, optimizing, so having the best sequence of units to be introduced and still spinning, I mean, like Chinese dishes, but still taking advantage of the network structure. So it's very simple. So for each node now we defined, I mean, not a number of repetition, but something slightly more complex, which is what we call the knowledge strength, okay? And for each node, this is a node property. So the knowledge strength is actually a property composed by 3 elements. So the first element is ki of t, which is just the number of repetitions. So the number of reviewing sessions of the specific concept or flashcards or whatever you want to consider. So this is very simple. And so at this stage, actually, you're not yet considering the network property. The second one is actually a very active effect, we called it, I mean, of the network. So suppose you are introducing for the first time a new item, I, okay, but this item is in the middle of a neighborhood in the network. In this neighborhood, there are already concepts already introduced, okay? So you may want to take advantage by the idea that you know already the neighborhood, okay? And perhaps you know already something also about this notion, even though this notion was never introduced properly to you. So this ki0 is actually, I mean, forget about the formula, but actually this is larger if the number of concepts already introduced has been large, and also their weights in the network is already large. So the more you know the neighborhood, the largest will be your initial knowledge strength. And then there is also a passive role, because suppose now you are repeating the item I, okay, then in principle you're also perhaps, I mean, reinforcing also the strength of the neighboring nodes. Okay, so in this case also the node J takes a reinforcement, okay, with a number which is smaller than 1. Okay, the number is not important. It's just the idea that basically you have the number of repetition and then active and passive roles depending on the network. Whenever you have to introduce new concepts, I mean, of course, you can have different strategies. We tried 3 different strategies. One is just random learning, which is just jumping, I mean, from one place to another in the network. So picking randomly any nodes not already introduced with equal probability. Then there could be a sort of preferential acquisition scheme, which is just, okay, going everywhere, but then selecting a node with the probability which is proportional to the degree, I mean, or the strength, depending on if you have a weighted or unweighted network. Or random surfing, and you will see the random surfing will be the most efficient for our purposes, which is basically with the given probability, which is in this case will be 90%. Basically, you do a preferential acquisition in the neighborhood of the last visited node. Otherwise, you just jump, I mean, somewhere else. So, okay, this is basically very close to what you do typically in PageRank, I mean, in terms of exploring the network. Okay, let's go to the results. I mean, Massimo, let me know, I mean, whenever I pass 20 or 25 minutes.
Yeah,
So
you already talked 15 minutes, so you have like...
Okay, yeah, I'm getting, I mean, very close. Okay, so the main question is, how does the graph topology affect the learning process? Okay, and I'll show, I mean, some tests about synthetic graphs, and then we go for real data to compare this. And in order to make the comparison, we look at basically two quantities. One is the coverage time, so how much time is needed in order to introduce n units in the system. So n units means n Chinese dishes all spinning at the same time. Okay, so without forgetting anything. And the other one would be n of t, which is the growth in time of the number of distinct units introduced, I mean, versus time. So the derivative of n of t will be the learning rate, while, I mean, tn would be the coverage time to get to a specific point. Okay, suppose you have to learn, I mean, 10,000 words in flashcards. How does it take? How long does it take in order to do it? Okay, so let's focus first on n of t, which is the growth and the number of units, so distinct units in the system. And here you see, I mean, different graphs. So we go from, I mean, bottom left, the Erdős-Rényi and the Barabasi-Albert, and then top left and bottom right is actually the uncorrelated configurational model, so very simple, non-correlated scale-free networks. And just for reference, okay, the red lines are basically the ones without graph, so without taking advantage of the graph structure. And you see, I mean, whenever you take advantage of the graph structure, the velocity of learning, I mean, is definitely much faster. There are differences depending on the kind of learning strategy, whether random learning, preferential acquisition, or random surfings. But in all cases, actually, you get an acceleration with respect to the no graph structure. This is interesting if we look actually at the coverage time. Again, I mean, we go for the Erdős-Rényi, Barabasi-Albert, and the UCM graphs with different exponent 2 and 3. You see, I mean, what is interesting is, for instance, if you look at the UCM with gamma equal to 2, which is the top right, you see that in the random surfing, so the green curve, the random surfing strategy, there is a minimum of this coverage time depending on the average degree. So it seems that there is an optimal structure in this specific case, I mean, allowing for the faster learning. Then of course, I mean, in real graphs, I mean, the structure is given. Okay, we don't decide the structure unless we do something that I will mention in a second. Okay, but I mean, at the first order, we can imagine the structure is fixed, and then we run the learning algorithm and see, I mean, how effective it is. Let's move now to real data. Okay, so we consider both the human brain cloud. You just saw, I mean, the pictures, and also we consider the English Wikipedia subsections devoted to basically STEM, so physics, chemistry, mathematics, biology, and so on and so forth. And okay, and here are the results. For instance, this is the results for the coverage time for the human brain cloud for the 3 different strategies. You see, I mean, random learning is not very effective. Preferential acquisition is more effective. Random surfing seems to be the most effective. Of course, in this case, human brain cloud is just one network, while on the x-axis, you see you have the average strength. Okay, so this is a sort of what-if experiment. The point is that the red circle is the actual system, and then we basically modify the system in order to reduce or increase the average strength, which means basically, if you go on the left, removing links from the system or adding links to the right. There are 2 cards on the right because there are 2 different strategies to increase links. So either you pick random links of non-connected nodes, or you try to close triangles, so increasing the clustering coefficient for the system. You see, I mean, what is interesting here is that the minimum in this situation seems to coincide with the actual system. So it seems the human brain cloud is already tailored for the optimal learning in this situation. I don't know whether this is a coincidence or not, so that's why we went to another system, and this is what happens for Wikipedia. So if you focus on the top left, this is the bare results for the all Wikipedia networks, so subsection of physics. You see, in this situation, the real system, so again is the red spot, does not coincide with the minimum. But then we realized that actually, probably in this network, there are a lot of dangling bonds, okay? A lot of nodes with only one connection. So we basically consider what happened if you consider the 2-core or the 3-core subgraph. So I mean, considering the graph in which all the nodes have at least 2 connections or 3 connections, and then of course you can go on K connection. You see, I mean, the more you do this, and the more you restrict to the core of Wikipedia, the more this core graph, I mean, is close to the optimal structure for the learning process. So, I mean, we were sort of puzzled by this, but I guess, I mean, this implies that, I mean, I wouldn't say this is a coincidence. I would say that perhaps the way in which we construct our information network, so the way in which we construct Wikipedia or the human brain cloud, is not totally unrelated by the way in which people are supposed to learn those concepts. So, I mean, I guess, I mean, first, a very preliminary conclusion would be that, of course, I mean, we can find an optimal way to sequence the material, okay? And of course, depending on the learning process, you can be faster or slower. But I guess more interesting, I mean, it seems that there are optimal conceptual structures for learning. And I would say that probably there is a co-evolution of this conceptual structures with the learning path, which basically pointing perhaps to a tutor student interactions, I mean, along the way. Because of course, I mean, the way in which the network of concept is constructed depends on the way in which the tutor presents and sequence, I mean, the presentation of new units. So these are partial conclusions, which I already anticipated. I mean, if I have 1 more minute, I just want to discuss about the perspectives, because I think there is a lot of work to do in this area. Probably, I mean, the community behind NetSciEd is already working on this, but I will be glad, I mean, to share this with you and also discuss with you, I mean, about possible sharing works. So one of the question is, can we imagine to construct learning paths out of this? And I guess this is pointing to a new role for users, okay? Because perhaps, I mean, users are not so able to write contents, at least not all of them. But I think, I mean, users are much more able to construct to lines, I mean, connecting the dots. It is, of course, I mean, we'll be pointing in the direction of constructing personalized learning paths. There are many possible examples, okay, already there. FreeRise and Duolingo, I'm pretty sure they're already using sequencing with some specific algorithm. But suppose now you want to learn something about everything, about Renaissance, okay, Italian Renaissance, and then perhaps passing a test about this. What should you do, okay, in terms of books, I don't know, exhibitions, movies, I mean, music here to listen. So what is the best, best sequence, I mean, for all this material? There was this interesting paper, I mean, a few years back about the human wayfinding in information networks. In this case, actually, there is a specific task because you have to go from A to B, okay? And still people have to find their way in this direction. But in general, this can be done, I mean, whatever is A and whatever is B. There was a service introduced, I mean, a few years back by Wikipedia to construct collections, okay? So already to put together a certain number of pages connected to a specific topic, and also presumably also considering, I mean, the specific sequencing of the pages. You can think about guided tours, okay, for this. But also you can think about, for instance, the way in which we write books or we construct, I mean, our courses. Of course, I mean, books are linear objects, but I mean, the way in which these are used by students, I mean, can be far from being linear. I mean, students can actually go back and forth depending on the sort of dependencies in the book. And perhaps the best books are the books that do not require, I mean, to go back, I mean, very, very often, because probably you forgot the concept because it was mentioned, I mean, too far back, or because, I mean, you needed a concept which is not yet introduced, and then you have to go back in order to find this concept. So I think, I mean, there are a lot of directions in which this kind of very, very simple, probably simplistic algorithms can be applied, and I will be happy, I mean, to hear about your comments. Thanks a lot. Sorry if I was too long.
No, you were perfectly on time. So let's thank the speaker for the talk. Thank you. And we have a few questions. So one of them was from Steve. Would you like to ask the question directly or should I read it?
Sure. So my question has to do with, and maybe it's not directly related to your work, but this idea of do you account for exogenous factors in you know, in the structure of how knowledge is handled, I guess, in the brain or mind, like you know, whether it's prior knowledge, which actually is not exogenous, but also things like social capital and you know, ethnographic factor, income, things like that. Whether you've thought of the things that might be barriers to knowledge outside of the mind and brain.
Steven, no, you're right. I mean, of course, I mean, when we speak about the conceptual network, we think that we have in mind something which can be common to everyone. But I guess this is far from being true. I mean, so each of us has in mind, I mean, as constructed, I mean, while learning from our childhood, I mean, a completely different network. And perhaps, I mean, when we learn, I mean, with the teacher, probably we are trying to have largest overlap between the network structure of the teacher and the network structure of the students. And in this clash, in this gap, probably the gap and Massimo was actually highlighting with the aura, there is all the game of the nice learning. So I don't have an answer for your question, but it would be interesting to see. Of course, I mean, the statistic can be difficult for individual people, but I guess it would be interesting to see how much these conceptual networks are different from different people. How do they evolve over time? So we did a lot of work with the notion of adjacent possible, which is a set of things you can possibly explore in the near future. And these kind of networks are totally different for different people. And it's interesting to see, I mean, how this network interact, and the fact that I interacted with you today can actually open for me a new perspective, and I would be exploring something I don't even, I mean, think about, I mean, before discussing.
Absolutely. We have another question by Professor Ismo Koponen.
Thanks, Massimo. Vittorio, thanks, very nice talk you gave, and I'm very convinced that one of the challenges and very interesting research topics is to find a certain kind of cognitive models, how these information networks and conceptual networks are built on. And one thing which I have been thinking about is that when we think about real individual learners, the starting point very often is that they have a vague idea of the importance of certain things, how things are related, and then they need to proceed through local rules to find out the word paths and to build and construct the networks. And we have collected some data from our students learning physics history, and it seems that the networks they build about the physics history are highly contextualized, and the thematic organization of the knowledge they have has an important role, but also the taxonomic relation. And that reminds me about the David Chandler's two-dimensional semantics, where he argues that actually conceptual knowledge and conceptualization proceeds in two dimensions, in thematic and in taxonomic. And have you tried to find out how such models where you use some of this kind of information performs as a model?
No, that's very interesting. I guess would be a direction to go. No, we didn't did it so far, but yeah, thanks for the suggestion. I guess could be a very interesting direction to go. I guess what could also be interesting is to find some empirical ways. I mean, to detect, I mean, the structure of the conceptual network and the way in which this changes for individual people. This is not easy. I mean, for instance, if you think about books, now we more and more have e-books, right? Okay, and nobody's actually checking, I mean, how people read these e-books. Okay, in many cases, you can actually annotate these e-books. You could actually check, I mean, whether people went from page 2 to page 3 to page 4 or jumping here and there. This will be a measure. Of course, I mean, it's a measure of two things. First, I mean, how good is the book? But of course, this you can actually rule out by comparing different people reading the same book. Okay, and then, I mean, how structured is the conceptual network of the individual person at different stage of their evolution. So I guess there could be a lot of empirical interesting results here. I mean, looking, for instance, at eye tracking. So how people, where people are actually looking in specific text. But probably mostly, I mean, how people jump here and there in this sort of linear structure.
Okay, thank you so much for the talk again. I really enjoyed it. Thank you so much.
I'll stop sharing.
I have a few questions, but unfortunately we don't have time, so